Right, so we'll go over the visual field pathways. So we're going to be looking at a superior view, so looking down at the patient, which means that their left eye is on our left side, then we have their nose, then we have their right eye on our right side, so it's not the same as anatomy. Everything is kind of the same on our side, not like in anatomy. Okay, so each eye can see the left side and the right side, so each eye has the left visual field, so the left eye has a left visual field, and the right eye, and also in purple, can also see the left hand side, and then the left eye can also see the right hand side, so it has a right visual field, and the right eye also has a right visual field in green, so the visual fields are the same color. Okay, also the ones that are closest to the nose, so the right visual field in the left eye and the left visual field in the right eye, those are called your nasal visual fields, and the other ones, so this one and this one, are called your temporal visual fields. Okay, so information is going to go from your eyeball to your retina, which is your first layer of is your layer of photoreceptors, first kind of stage in this pathway. So the retina basically is where you're going to have your first kind of crossing over. So your right visual field is going to go to the left side of the retina. Your right visual field is going to go to the left side of the retina. Your left visual field is going to go to the right side of the retina. Your left visual field is going to go to the right side of the retina. So you have one crossing over already. Okay, then what's going to happen is these fibers are going to leave the retina via something called the optic nerve. Okay, the optic nerve basically contains all that information from both visual fields in one eye. So obviously, you can imagine, and that's cranial nerve 2, by the way, you can imagine that if you have a lesion here, basically none of this information is going to make its way into the occipital lobe, so you're going to have complete loss of vision here, aka binocular blindness. Okay, then what's going to happen is you're going to have, these are going to form the optic tract. So what happens? The optic tract contains contralateral visual field information. So on this side, the left optic tract is going to contain information from the right visual field. So the right visual field is this one in green here, which can continue down this way, but also on the right eye is this one in green here. However, this one will need to cross the midline and then go to this side to form the left optic tract. So the right visual field has crossed to form the left optic tract. And on the same side, we have the same thing on the other side. So on the this here is your left visual field. So on your right eye, your left visual field is gonna go here and then form your right optic tract. But on the other eye, on your left eye, it needs to cross over. The left visual field needs to cross over to form the left optic tract, the right optic tract, which contains information about the left visual field. So basically, we have crossing over. And you may notice that it's actually the temporal fields of vision that have crossed over. And they cross over at something called the optic chiasm, which sits underneath the pituitary gland. What can happen is you have enlargement of the pituitary gland called pituitary adenoma, links with like hormone stuff. And then basically this can compress that and stop your temporal lobe's information from crossing over and reaching their optic tract. So as we can see here, this forms the left optic tract, which contains information from the right visual field in both eyes. So if we have a pituitary adenoma, what's going to happen is this crossing over is going to be finished, and essentially we're going to lose this half and this half, basically the temporal lobes. So it's called bitemporal, temporal lobes in both eyes, hemianopia, half of the eye is gone. And this is often due to a pituitary adenoma. Okay, and then we can see here after the crossing, we've made up our optic tract. So again, the right optic tract contains information from the left visual field in both eyes. Okay, so what's going to happen now if you have, so the optic tract is going to contain this green, or this purple and this purple. If you have a lesion in, say for example, this side, then you're going to lose this green and you're going to lose this green in both eyes. So in both eyes, you will lose the same visual field. And it's going to obviously be opposite because of the crossing at the retina. It's going to be opposite on the contralateral side. So this basically, if you have a lesion in these greens, you will have loss of this space here. So contralateral on the opposite side, homonymous on the same side in each eye, hemianopia, so half of the eye is gone. And that's an optic tract lesion. Okay, then our optic tracts are going to connect to our thalamus, which is kind of in the middle of the brain. And the thalamus has connections called reciprocal connections to the rest of the brain, so the occipital lobe. And then basically from those connections, more visual information is going to basically go. Right, so they're going to go to a bit of the thalamus called the lateral geniculate nucleus, the LGN. Auditory information goes to the medial geniculate nucleus, so M for music, L for light. So this goes to the lateral geniculate nucleus in the thalamus, which is kind of at the back of the thalamus. The thalamus has two lobes, so there's actually two LGNs, but there's one thalamus but two lobes. Okay, now the thalamus, as we said, has reciprocal connections. These, in terms of vision, are called radiations, optic radiations, and it's going to divide the visual field information not only into left and right, but also into up and down. So it's going to have superior radiations and inferior radiations. And just like left and right is going to swapped, so the contralateral here, up and down is also swapped as well. So what happens, just because your eye's weird, so what happens is information from your inferior visual field goes to your superior radiations, and information from your superior visual field is going to go through the temporal lobe underneath, and that's called the inferior radiations, to your occipital lobe. And this one in purple is the one that you probably need to know more about, and it's also called Meyer's loop. So here we can just see the radiations, the inferior ones here in darker, and then the superior ones in lighter, and they're going to V1, the cortex, which is supplied by the PCA. So the superior radiations pass through the parietal lobe, and they contain inferior visual field. Okay, so if you notice, the optic tract contains two kind of fibers, right? That's why we divide the eye into two. Or there's 4 fibers in total, so 4 segments in total. However, there's 1, 2, 3, 4, 5, 6, 7, 8. So we're going to have to divide the eyes into 8. So instead of looking at just left and right, we're looking at quadrants now, which helps to understand the pathology. And you can think more about the quadrants like this. Okay, so this is the right-hand side, which means it's supplying, this dark purple here is supplying the left visual field. Okay, and the light purple, the pink here, is also supplying the left visual field because it's on the right side. Okay, but the dark purple is inferior, is the inferior radiation, which means, again, you flip it, so the inferior radiation supplies here, the superior visual field in both eyes, so this is because this is on the right hand side is supplying the left visual field, superior, and then the pink one here is going to also supply the left visual field, but remember it's superior, which means it's the inferior visual field in both eyes. And then we have the same for the greens. We have the superior on the right, so it's going to be on the right visual field because it's on the left side, and it's going to be superior because the inferior loops will be superior visual field, and then the superior radiations in light green will be the inferior right visual field. Okay, now, so say for example, what happens is if you draw a line through all these green ones, so 1, 2, 3, 4 are all KO'd, well, basically, none of this information will be able to come from this one, so lost, and none of this information will be able to come from this one, lost and lost. So therefore, it's the same thing as an optic tract lesion. It's contralateral homonymous hemianopia in the other eye. Okay, but the other one that you need to know about is not if all of them are lost, what if just one optic radiation is lost? So for example, in the inferior, what if the temporal optic radiations are lost? So what's going to happen here? Let's work through it. Say, imagine you lose the inferior optic radiations on your right hand side. So your right hand side, they are going to supply the left visual field. So this guy's here, and inferior radiations meaning the superior visual field. So if you lose those radiations on your right hand side, your inferior right radiations, then what's going to happen is you're going to lose basically the top quadrant in both of them. However, just kind of like a minor point, because this is on the right hand side, you don't really need to know the detail behind it. Because it's on the right hand side, the right eye is more affected, and the left eye kind of has can get visual information from other areas as well, because of the thalamus. Like stuff kind of information kind of flows differently in the thalamus, so it kind of sorts over. So the left eye is less affected. So it's called pie in the sky, because this left eye forms a pie. But you can imagine it. If you're stuck, just think of it as 2 quadrants gone, and then obviously, just to be technically correct, it's pie in the sky. And then obviously, if this is on the other side, it will just be the inverse. So the left eye will be fully affected, and then the right eye, this bit here, will have pie in the sky. You don't need to worry about if these ones are damaged, but it's basically the same thing. You can work it out. It's called pie on the floor. So again, the side of the lesion is more affected. Okay, finally, we are going to talk about the PCA stroke, the occipital lobe stroke. To do that, we need to bring up our assistant Patrick Starr. So this is Patrick. This is his right side. Now we're looking anatomically. So this is his right side. This is his left side, which he's been helpfully color coded right. So we are going to we're going to move Patrick, and we're going to lie him down so that he can lie onto our CT scanner. Okay, so Patrick is now lying down like this. Now our CT scanner is how it takes an image, or this can also be an MRI, it's going to slice down this way. So if we imagine it's like a knife slicing down this way, as it's slicing, the image is being formed, And therefore, so we're viewing the image from his feet, and therefore we get this image where Patrick's right side of the brain is on our left side, and his left side of the brain is on our right side. So it's kind of just like a normal anatomical diagram. So therefore, if we have a look at this stroke, basically it's showing you that CT scans are like any kind of brain scan is going to be inverse. So this here is the patient's left side, this is the patient's right side. And again, we're looking for symmetry in strokes. This was obviously CT scan because of the bone here. And obviously this big black blob is occlusion. It's not symmetrical. So obviously there's something wrong here. And therefore it's a left-sided PCA stroke. Okay, left-sided PCA stroke. So basically, remember, obviously you have an occipital lobe in both hemispheres. If it's lost in your left hemisphere, essentially what happens, the left hemisphere is going to take information from the right visual field, okay? Because it's basically all flipped. So that's the whole point of this flipping, is that the hemispheres go to the opposite lobe, following the same way as the optic tract. So left hemisphere, left stroke here is going to be a damage to the right optic field. So it's going to become something like this, okay? Forget that it says optic tract lesion, but a PCA stroke will cause, in the left side, will cause contralateral, so on the right side, homonymous hemianopia, okay? However, it's not exactly like that. It's basically like that. However, the bit in the middle, with a PCA stroke only, is not actually affected. And this is called macular sparing. This is a really important detail that you have to see. So it's essentially the same thing as this. However, the PCA, the V1 cortex, is not only supplied by the PCA, it's also supplied, because it's really important, the middle bit where your vision is focused is supplied by something called the ophthalmic artery. So therefore, obviously, the ophthalmic artery is not going to be affected as well. So therefore, this middle bit is actually saved. So you're going to get contralateral homonymous hemianopia, however, with macular sparing. Okay, this bit is confusing. So whenever you're looking at a CT scan, you need to think, what side of the brain am I looking at? Okay, and then you can either draw the pathways from there. So from here, you can draw the pathways or look at the hemispheres, or just know that it's going to be the opposite side of the hemisphere. So this is a left-sided stroke. So therefore, the visual field is going to be lost on the right side with macular sparing. And that is everything.